Hey guys, Dr. Cadell here. This is the Empirical Formulas Lab. Two parts to this lab, guys. The first part is the zinc iodide portion, where you synthesize the zinc iodide, and from your data, you're able to calculate the empirical formula for zinc iodide. Now, we know that the true formula is ZnI2. That's not the point of this. The point is, how can you figure out the formula of this compound just from your data from your experiment? I'll tell you how you do that in just a minute. The second part of this lab, it's the hydrate. What you're going to do there is you're going to get a hydrate, which I'll talk about in a few minutes, and you're going to determine the formula for that hydrate. We'll get to that in a minute. So let's talk about the zinc iodide. Let's pretend we don't know that it's really ZnI2. We say, okay, zinc iodide has zinc atoms in it and iodide atoms in it, and the goal is to figure out what these subscripts are, what our X and our Y are. Now, what they are, it's the ratio of the moles of iodine to the moles of zinc, or you could do it the other way around, but we'll do it this way. Now, so what that means, guys, is that in order to calculate our subscripts here, we need to know two things: how many moles of iodine there are in that formula, and how many moles of zinc there are in that formula, in that compound. So here's how we do it. The way this lab is set up, you're going to react zinc with iodine. And it's set up so that iodine is by far the limiting reactant. That means that the iodine will be all used up. There's not going to be any iodine left at the end. There will be excess zinc. That makes the iodine calculation really easy, because we're going to weigh out the iodine. We'll know, right, how many grams of iodine we have, and all we have to do is divide the mass of the iodine that we weigh out by its molar mass, and that gives us moles of iodine. To get the moles of zinc, it's still not too bad. The way it's set up is because zinc is in excess, there will be some zinc left over at the end of the experiment. So what we do is we weigh how much zinc we start with, and then at the end, we're going to collect the zinc that's left over, weigh it. And that means that the difference in the mass between how much zinc we start with and how much zinc is left at the end, that difference is how many grams of zinc reacted, which is what we need to know. Because to do that, to calculate the moles of zinc reacted, all we do is take the grams of zinc reacted, divide by its molar mass. So right, once we do that, we'll know the moles of the iodine and the moles of zinc. Take this ratio, and that will give us how many Y's there are for every one X. So in the second part of this experiment, you're going to determine the formula for a hydrate. Now, so let's talk a little bit about what a hydrate is. A hydrate has basically two parts. There's an ionic compound, just a regular old cation and an anion, and then there's some water molecules associated with it. Now, a couple things about hydrate. First of all, it is definitely a solid. A lot of times people see the water and they think, oh, that's a liquid. No, it's a solid. And what it looks like, if you could see the individual atoms in this compound, it's pretty cool. What you would see is that the cation and the anion arrange themselves so that all of the cations are as far away from each other as they can be. Same thing with the anions, away from each other, but the cations and the anions try to get as close to each other as they can. And that's basically because of Coulomb's law. Opposites attract, likes repel. And just because of that, they arrange themselves in this very ordered structure at the atomic level. And it's like they're at the vertices of a lattice. Like if you've ever seen a scaffolding that painters use to go on the sides of buildings, where the pipes intersect would be where the atoms are. Now that's important for us because in a hydrate, the water molecules, they're kind of stuffed in those openings between those points within the lattice. And what's another thing that's important is that the strength with which the cations and the anions hold each other together is pretty strong. But the strength with which the water molecules are held is much weaker. And we're going to take advantage of that in this experiment to drive off those water molecules without affecting the rest of the compound. So there's two things that we have to determine to figure out what the formula for your unknown hydrate is. One thing is what the formula of the anhydrous salt is, which is the ionic compound. So here's some terms. When we have the hydrate with the water molecules still attached, stuffed in those spaces within the lattice, we call that the hydrate. And one of the properties of hydrates, by the way, is that if you heat it up enough, those water molecules leave. And what's left behind is the anhydrous salt, which is just an ionic compound without those water molecules. And the water molecules leave as steam, as water vapor. So to determine what the anhydrous salt is, we're going to start with what's called a flame test. And it's just like it sounds. You're going to take some of your unknown hydrate, stick it in a flame, and look at the color of that flame. And here's how that works. So if we're going to go over here and look at these formulas over here. Another thing that's going to help you guys is that it's limited to 4 possibilities as to what your hydrate can be. Strontium chloride, a hydrate of it, potassium carbonate, hydrate, zinc sulfate, or magnesium sulfate. So to determine what the anhydrous salt is, that's the identity of the ionic compound in the beginning. Like we said, we're going to do a flame test. So you take some of your hydrate, stick it in a flame, which I'll demonstrate for you. If you see a red flame, that tells you that you have strontium in there, because strontium atoms, when they're put into a flame, they give this really vivid, beautiful red color. It's really obvious, and you'll see it. If you see that red color, you know that there's strontium atoms in there, and that means that your anhydrous salt is strontium chloride. Well, what if you don't see red flame? Well, there are potassium atoms that ends up, when you put those into a flame, they give off this light purple color, kind of like a lavender color. And so if you see that color, which I also will demonstrate for you, you'll know that you have potassium atoms in your unknown, which means that your anhydrous salt is potassium carbonate. Well, if you don't see either of those 2 colors, then you're lucky enough to be able to do what's called the magnesium strip test. And what that is we just take some of your unknown hydrate, put it in some water, drop a strip of magnesium metal in there. And what happens is if your unknown is zinc sulfate, the anhydrous salt, you're going to get this black coating on the magnesium metal. And so if you see that black coating, you know you have zinc sulfate. Because remember, you only do this if we don't get any color on our flame. So we've eliminated these 2. There's only 2 possibilities left. You see the black coating, we know you have zinc sulfate. Well, if you don't see that black coating, there's only 1 possibility left, magnesium sulfate. Now you know what your anhydrous salt is. So let's talk about the other thing we're going to figure out about your unknown hydrate, and that is how many waters there are associated with each formula unit of the ionic compound. So if we look back over here, this number, okay, I'm using an example which is not one of your unknowns, by the way, cobalt 2 chloride hexahydrate. In this example, there are 6 water molecules for every 1 cobalt 2 chloride. And this number is the second thing we need to find about your unknown. And what that number is, that tells you the ratio between the moles of water and the moles of your anhydrous salt. Now, it does not necessarily have to be a whole number. In the first part with the zinc iodide, yeah, we can't have fractions of an atom, so the subscripts in the formula, the empirical formula, have to be whole numbers there. But here, it's not. It doesn't have to be a whole number. So the way to get this number is if we know how many moles of water we have and how many moles of your anhydrous salt, we just take that ratio, that gives you our X, or our number in front of the water. So that means we need 2 numbers, moles of water, moles of the anhydrous salt. So moles of the water, it's just the mass of the water in grams divided by the molar mass of water, which is this. To get the grams of water, what we're going to do is we're going to weigh your unknown hydrate before we heat it up. After we heat it up, we're going to weigh the mass of the anhydrous salt. The difference between the mass of the hydrate, which is with the water, and the mass of the anhydrous salt, which is without the water, is the mass of the water. That's pretty easy, and that gives us our top number, divided by the molar mass, and there are our moles of water. Now to get the moles of the anhydrous salt, that's easy too. Once we've determined the identity of our anhydrous salt, we can calculate its molar mass. We also will know, because we'll have weighed it, how many grams the anhydrous salt weighs at the end. So we just take that mass, divide by the molar mass of the anhydrous salt. We have the moles of the anhydrous salt. Put it in here, get our ratio. That's what goes there. And that's all there is to it. So why don't we go over here and get started on the experiment. All right, guys, so we're going to start the first part of the experiment, the synthesis of zinc iodide and determination of its empirical formula. First thing we need is the mass of your empty 150 milliliter beaker. So make sure the balance says 0. Place it on the balance, close the door, record that number, that goes in your data table. Then with the beaker still on there, we're going to tare the balance. Now it says 0 with the empty beaker on it. So we take the beaker out, making sure not to touch any buttons. We're going to add about 1.2 grams of zinc first. Now, a couple things about adding these reagents. Matt will have some spoons out. He has what that spoon is for on it. This one has zinc. This one is for iodine. And that's important because if you mix these up, you're going to contaminate the whole bottle. What has happened in the past is people have used the spoon for iodine in the bottle for zinc, and we come back the next day and this whole bottle is discolored. It's obviously contaminated. So we want to be really careful about that. But we add the zinc first. So we want about 1.2 grams. And it's not really that much. Now, remember, zinc's in excess, so if we put a little bit too much, that's not a problem because we're going to weigh how much we have at the end anyway. So there we go. Close the door, record that number, that goes in your data table too. That's the mass of the zinc that we have initially. Then, now that we have that mass, tear out the balance. So now the balance says 0 with the beaker and the zinc on there. Take it out. Now we're going to add the iodine. We have to be kind of careful with this because once we put the iodine in, we can't take it back out because it starts reacting as soon as it hits the zinc. And it really doesn't take as much as you think. It's in the form of these little tiny spheres. So just go a few spheres at once. And there we go. If it's a little bit over, that's okay because the way this is set up, zinc is in excess by far. I'm going to put the lids back on this. And just to remind you guys, remember, you never add anything directly on the balance. The iodine here, if it gets on the pan of the balance, it'll ruin it. So we've got that number in our data table. To get this reaction started, we're going to take about 5 milliliters of 0.2 molar acetic acid, put it in there. Now it's going to start reacting. Just give it a little swirl. And we're going to set this aside now and start the second part of this experiment while we wait for this to react. But let me just tell you what you can expect to see. Right now, it's just starting to turn a little bit yellow because that's what that is the iodine starting to dissolve in the acetic acid. Pretty soon, when more of the iodine dissolves, it'll become this dark red color. Now, we're going to set that aside and let it react. But we'll know when this reaction is finished because remember, the iodine is the limiting reactant, and the iodine is what gives the solution that color. Well, once all of the iodine has reacted, this solution will be clear again. It'll look just like water. And so our test to make sure that all the iodine is actually reacted is we put this on a piece of white paper, and if we see even a hint of yellow, that means it's not quite finished and we want to let it go a little bit more. So we're going to set this aside, and we're going to pick it up every minute or so and just give it a swirl. So let's put it right here. Doesn't matter. Now we're ready to start the hydrate portion of the experiment. So the first thing we're going to do is take our crucible with the cover, empty, clean. Make sure the balance says 0. Place both of these on there. Record that number in our data table. That's the mass of the empty crucible with the cover. Then what we do is we take the cover off, tear the balance, because what we're going to do now is weigh out our unknown into the crucible. So our unknown comes with an unknown number. Make sure you take that off and record that in your data table also. So 0 with the empty crucible. Take it out. I'm going to add about 4 grams or so of this. Close enough. So record that number in your data table. We're going to need some more of our unknown hydrate to do the flame test in a bit. Now what we do is we take the crucible lid, put the cover on, leave a little crack, just like that, and place it on the hot plate. The hot plate should be turned up about halfway. And we have to keep our eye on the crucible for the first 5 minutes pretty carefully, because what happens sometimes is as the water molecules start vaporizing and leaving, they form these bubbles that pop, and then stuff starts shooting everywhere, and we want to avoid that. What does happen, what you'll do, if you do see some popping, you'll take some crucible tongs, put the lid back on the crucible, turn them over, take it off, set it on your wire gauze, just till the popping stops, and put it back on. And keep doing that until the popping stops. After the first 5 minutes or so, you won't have to worry about that. So after the first 5 minutes, what we're going to do is turn the heat up all the way and let it stand there for 15 more minutes. At that point, we'll take it off and weigh it. So we'll get to that in a minute. While we're waiting for this to happen, let's go over and look at our zinc iodide. See how it's gotten a dark red color? The iodine is starting to dissolve, and now we're waiting for it to all react with the zinc. So set that aside. What we can do now is the flame test. So for the flame test, you're going to use a Bunsen burner, which you haven't used yet, so I'm going to demonstrate how to use it. Well, a Bunsen burner comes with a hose attached, and the hose attaches to the gas outlet, which has the blue cap on the top. This goes right there. A Bunsen burner basically has 3 controls, guys. The first control is the handle on the valve. And this handle, if it's perpendicular to the nozzle, either way, that means that the gas is off. It doesn't matter which way. If it's perpendicular to the, parallel with the nozzle, that means the gas is on. And that's all you use the handle for, either to turn it on or turn it off. The second control on the Bunsen burner is this knurled handle on the bottom. This is a needle valve that controls how much fuel, how much of that gas gets to the flame, which is up here. The more this is turned in, the less fuel gets to the flame. The more it's backed out, the more fuel gets to the flame. Now, the only thing you have to watch out for, guys, is if you back this out really far, and you really have to back it out a lot to do that, and this is lit, what happens is this comes out, and now flames are shooting out the bottom of this Bunsen burner right at your hand. So, to avoid that, what we do is when you first get your Bunsen burner, you're going to take that knurled handle, turn it in all the way till it's closed. We really don't need it backed out much to get a good flame. So once it hits the end, we're going to open it one turn, about 360 degrees. About like that. And then we'll adjust it once we light the flame. And the last control, the third control, controls how much oxygen, which comes from the air, gets to the flame. And that's this little gap at the base of the column right here. Now, we control that gap by opening or closing this. This also, by the way, will come off. That's not a big deal, because if this comes off, the flame goes out. However, if this is open too far, there's too much oxygen and the flame keeps blowing itself out and you can't get the thing lit. So a good starting point is if we have, about a millimeter or so between the top of the threads and the bottom of the top of the gap, about like that. So now it's set up to light. So we take whatever we're going to use. You can use a striker, matches, barbecue lighter. Turn on the gas, bring the flame up from the side. Now we have a flame. We still have to adjust it, guys. That flame needs either more oxygen or less fuel. I can tell because this is big, huge thing, and we want to, I'll show you what we want. We want this bright inner blue cone. So what I'm going to do is I'm going to decrease the amount of fuel. Remember, that's this right here, so I'm going to turn this in. And then it's still not what we want, so I'm going to give it a little more oxygen by opening the gap at the bottom. And go back and forth, maybe give it even less fuel. And there. So if you can see that bright blue inner cone, that's what we're looking for. And by the way, the hottest part of this flame, it's the very tip of that bright blue cone. right there. Usually that's where we want to put stuff. All right, so we're ready to run our flame test. What you do is you're going to take your unknown hydrate that's in your test tube and get a wood splint. So wood splint's just a coffee stirrer. Get it wet. And I'm going to show you what all these look like. Getting it wet, it just helps your hydrates, stick to it a little better. So I have about that much of my unknown hydrate on the wood splint. Stick it right in the hottest part of the flame. Remember, we're looking for red or purple, right? Oh, look at that. So that red flame there tells you there are strontium atoms in there, which means you know what your anhydrous salt is, strontium chloride. All right, let's look at something else. By the way, it's been 5 minutes, so what I do is I'm turning up the heat on my hydrate. Put this in the flame. See that purple color right there? That tells us we have potassium atoms that are unknown, and that means that our anhydrous salt is potassium carbonate. Now, if you don't see either of those two colors, then you get to do the magnesium strip test. So we're finished with the flame, so we just turn it off here, set it aside. The top's going to be hot, the bottom's not. So now we're ready for our magnesium strip test. So take a small test tube from your locker. Take your unknown. Again, this comes from the test tube that you got your unknown in. And you don't need really very much at all. Just that much is plenty. Try not to spill it like that. Take some deionized water. Add about like that, it's fine. Give it a little shake, make sure it's going to start dissolving. Then we take a magnesium ribbon, just a little tiny piece of magnesium. We only need one, they're pretty small. So it's important, by the way, to remember what it looks like. It's this shiny silver metal. And put it in there. So we have two. Now, it's going to take a few minutes to react. So we're going to set it aside and let it react. But remember, what we're looking for, guys, is if we get this black coating on the metal, that tells us our unknown anhydrous salt is zinc sulfate. If we do not get that coating, that means it's magnesium sulfate. If you can see, there's some bubbles coming up. That's a side reaction. Magnesium reacts with water. We don't care about that. So we're going to set this aside, and we'll come back. We'll look at that a little bit later. Let's check in on our zinc iodide. Still dark, so still have a ways to go. Let that finish reacting. Our hydrate's heating up. Now we just have to wait a few minutes. All right, guys, now we've been heating this crucible up for full 20 minutes, 5 minutes halfway, 15 minutes all, the full way. Now we're ready to weigh it for the first time. Put the lid back on, take it off, set it on our wire gauze until it's cool enough just to pick up by hand, then we'll weigh it. While we're waiting for that to cool, come back, look at our zinc iodide, we can see that all the iodine has reacted because the solution is completely clear now. So what we're going to do now is we're going to wash the zinc. So first thing we're going to do is decant the solution off the top into a waste beaker. We're not trying to get all the solution off, just as much as we can. Our goal is to try not to let any of the zinc or as little of the zinc come over as possible. So I have some floating it there, and it's starting to already come over, so I'm not going to worry about it. I'm going to take about 3 milliliters of some acetic acid. And exact volume is not real important, so I'm just going to use a transfer pipette. Get about 3 mils. Squirt it in there. Give it a little swirl. Let it settle down. This is washing the zinc. Pour it off. Again, we don't have to worry about getting it all. Do that 2 more times, so 3 more mils of acetic acid. Give it a swirl. Pour it off. Zinc. We're going to do that a total of 3 times. Then all we do is we wash it with water 3 times. So you just squirt about 3 mils of water in there, swirl it, decant it 3 times. At that point, it's still going to be wet. There's going to be some water in there. We don't care. We're going to take this, we're going to set it in the oven, and we're going to leave it till next week. When we come back, we'll take it out. It'll be plenty dry. We'll weigh it, and that's all we need for this part of the experiment. All right, guys, so now that the crucible and the cover are cool enough to pick up by hand, we're going to go weigh it on the balance. This is our first time weighing it after the heatings. Make sure the balance says 0. Place the crucible cover with anhydrous salt on the balance. Record that number in our data table. Now all we do is we come back, place it back on the hot plate, which is still on, full blast. Crack the lid a little bit. Heat it up for about 10 more minutes. Take it off. When it's cool enough, weigh it. And we're going to compare those 2 numbers. If those two masses are within 0.01 grams of each other, that means that we're finished. We can be sure that we drove off all the water and we can stop. If not, we're going to heat it another 10 minutes, weigh it, and compare the 2 most recent masses. If they are close enough to each other, within 0.01 grams, we can stop. Shouldn't have to do that more than 2 times. But we want to definitely get within 2 consecutive weighings within 0.01 grams of each other. Once we get that, we have everything we need for this experiment, and we're finished.